first, yeah.
Hello. For this lab, we're going to be using OMSAT to compare the series and parallel connections using a voltage current graph.
Okay, so for the materials we're going to use for this lab are going to be 3 resistors, a few cables, let's see, this voltage provider, and the Pascal 850 universal interface to measure the voltages. And we're going to use this to calculate the measurements.
Procedure for step 1. So we start by connecting these, and then we're going to connect them to the resistors. This is the resistor 1, and we're going to get the experimental value for it. ¿Importa el lado, tú crees? No sé. We're going to do it for the second resistor as well to get the experimental value, since we already calculated the theoretical value. And for the third resistor.
They're so sad. That one was
There we go. So for part 2, we all concluded that the B, the series circuit, will have larger resistance because it's a longer continuous circuit rather than A, which is shorter, but it cuts off several places. So for part A, for the parallel, we're going to connect all 3 resistors. And then we're going to measure the experimental value of this. Yeah.
Okay, so we are adding the amount of voltages we're passing through this. That's going through the resistor right now, and this is what we are given. And we're gonna do it for each of the 3 resistors.
After we recorded the circuit in parallel, we're going to record it in series. So that's the series. Oh, nope. So for step 5, we conclude that the order of the resistors does not matter. Either when it's in parallel and you have 1, 2, 3, or 2, 1, 3, or 3, 1, 2. The answer should all yield the same result. Likewise, when it's in series, as long as it's in the same series, the order of the resistors will not matter, and we will prove this in step 6. So in step 6, we have 1 as parallel to 2, and then we have 2 and 3 as a series, and we're going to measure the resistance of this. Okay, so for the 6th step, we already did the value for number 2, because number 2 is the one in series. This is 1 and 3. So now we're going to do the value for number 1. So we're going to rearrange this. We're going to put 1 in series. We're going to put 2 and 3 in parallel.
491 you gave me right now.
In parallel, and then we're going to measure these values.
I'll be explaining the data analysis part. So first we have our first tables. So this isn't any data that we came up with. This is just a guide to how we can check what the resistance is based on the color on the bands. So first, using these tables, what we did was calculate the resistors and the theoretical values for it. So the first band was orange, which meant 3. The second band was white, 9. Band 3 is just the meaning of how many zeros there are after these first 2 numbers, and it's 1 because it was brown. And then the 4th band was silver, which is plus or minus 10%. And then the theoretical value from it is 390 plus or minus 10%. And then for the second resistor, it was red 2, violet 7, brown 1, silver plus or minus 10%. And then our theoretical value is 270 ohms plus or minus 10%. And then resistor 3 is green, blue is 6, and brown again, and the silver again plus or minus 10%. And our theoretical value for that is 560 ohms plus or minus 10%. Our next table, we actually conducted the experiment and we were able to get the graphs from Capstone. So our experimental value was 336, and from the table before, our theoretical value was 390. So our percent error was 14%. And then for our resistor 2, the experimental value was 254 and theoretical value was 270. For resistor 3, the experimental value was 592 and our theoretical value was 560, and our percent error was 5.71. So for our experimental values, we were able to get that from Capstone and we used the slope of it. So for our next table, we have the theoretical equivalent resistance. So for the parallel series, we calculated that, which is 1 over 1R1 plus 1 over R2 plus 1 over R3. So that gave us 116.25. And then for our series, we calculated that with R1 plus R2 plus R3, which gave us 1,182. And then for our next table, we conducted the experiment again to test out our theoretical values, and using Capstone again, we did the same thing. So for our theoretical value for series, it was 1,182, and then our experimental was 1,220, and our percent error for that was 3.21%. And then for our parallel, which we got before, was 116.25, and our experimental value was 122. So that equaled into a 4.95% error. And then for percent error in all series and in all parallel connections, our experimental resistor value for resistor 1 again was 336, which came from our theoretical value. Resistor 2 was 254, resistor 3 was 592. For our overall setup resistance, our resistor 1 gave us 513.74, resistor 2 468.35, resistor 3 736.651.
These are the results we expected, because when all the resistors are in series, it's going to give the greatest amount of resistance and the least amount of current. And with only one resistor being in series while the others are in parallel means that the total resistance is less because the two other resistors are in series. What is the relationship between the series resistor and the overall value? So the resistor that is in series adds to the resistor in parallel, but in this case, the resistors in series are resist more than the ones in parallel.
On conclusion, in this lab, we learned to compare the resistance of a series and parallel connections by calculating the resistance using the slope of a voltage versus current graph. We also learned that each resistor has its own color code and that each color has its own value. We also learned that the order of the resistance does not matter.
My name is Gabby, and I did all the data and analysis part of the experiment.
My name is Gabriela, and I did the procedure.
My name is Emily, and I did the conclusion.
I did the introduction and I recorded and edited the video.
I did procedure and materials.